సే పార్ట్ 2 ఫ్లాయిడ్స్ వార్షెల్ అనమాట. Floyd's Warshall. The strategy adopted by the Floyd's Warshall algorithm is a dynamic programming. The running time of the Floyd's Warshall algorithm is determined by the AAA nested for loops of lines 3 to 6 for execution of 6 lines takes off one time. These algorithms runs off n cubic triangle ఉంది అండ్ ఇది 1 2 3 అటు డి వాల్యూస్ 1 2 3లో ఉన్నప్పుడు కొన్ని చోట్ల ఇన్ఫినిటీ వస్తుంది, కొన్ని చోట్ల టైం వస్తుంది. డయాగ్రామిక్స్ 2 ఆఫ్ n3 అంటున్నాడు. ఇది ఎక్స్ప్లెనేషన్ చూడాలి.
Let's understand how the Floyd-Warshall algorithm finds the shortest path between any two pairs of nodes in a graph. Earlier, we've seen single-source shortest path algorithms, like Dijkstra's and Bellman-Ford. If you're not familiar with those, I suggest checking them out first, as they provide a solid foundation for understanding shortest path algorithms. Those algorithms are designed to find the shortest path from a single-source node to all the other nodes. For example, from node A to all the other nodes in the graph. But what if we want to find the shortest path between all pairs of nodes? One approach could be to run those single-source algorithms on each node once. However, this method can be inefficient, and that's where the Floyd-Warshall algorithm comes to the rescue. This algorithm operates on the adjacency matrix of the graph, where each entry represents the weight of the edge between two nodes. If no direct edge exists, the entry is set to infinity. Now let's name this matrix M0, and we need to initialize another matrix, T0, known as the predecessor matrix. This matrix keeps track of the previous nodes in the shortest paths and will be used to construct the shortest path between any two nodes. The core idea here is to systematically visit each node and check if it can act as an intermediate point to provide a shorter path between any two nodes. If such a path exists, we update the matrices accordingly. This process is repeated for all nodes in the graph. Let's find the next matrices in the following iteration. Keep in mind, the matrices shown below are purely for demonstration purposes. In reality, only one instance of these matrices exists and gets updated dynamically. This visual breakdown is just to help you understand how the algorithm works. Let's start finding shorter paths via node A first. The rows and columns connected to A will not be updated because they already represent the direct connections. Additionally, the diagonal elements will remain unchanged, as updating them would imply the presence of a negative weight cycle. If you're unfamiliar with negative weight cycles, I recommend checking out our video on the Bellman-Ford algorithm for a detailed explanation.
आप सब मेरे लिए काम करेंगे,
करेक्ट.
रिसर्च एनालिसिस करके स्टॉक्स रेकमेंड करेंगे.
I recommend checking out our video on the Bellman-Ford algorithm for a detailed explanation. Now, let's see how the updation works. First, let's check the path from B to C. The current cost for this path is 2. We'll check if a shorter path exists via node A. First, going from B to ACE, there is an edge with a weight of 3. Next, we check the cost of going from A to C, which is infinity, meaning there is no path from A to C. Since there's no shorter path through node A, the previous edge with a weight of 2 remains the shortest path. Next, let's check the path between B and D. The current shortest cost to reach D from B is infinity, meaning there's no direct path. We'll check if a shorter path exists via node A. First, the path from B to A has a cost of 3, and the path from A to D has a cost of 3. Adding these, the total cost becomes 6, which is less than the current shortest path of infinity. Therefore, we update the cost to 6 and set the previous node to A, as the path to D goes through A. Next is the path between C and B. The current shortest cost to reach B from C is infinity, meaning there's no direct path. We'll check if a shorter path exists via node A. First, the path from C to A has a cost of infinity, meaning there's no path yet, and the path from A to B has a cost of 2. However, the total still remains infinity, so we won't update this one. Next is the path between C and D. The current shortest path has a cost of 4. The path from C to A has a cost of infinity, and from A to D is 3. Since this is more than the current cost of 4, we will not update it. Next is the path between D and B. The current shortest path has a cost of 6. However, if we go via A, the cost from D to A is -2, and from A to B is 2, giving a total of 0, which is less than the current cost. So we update it to 0 and set the previous node to A, since the path is coming via A. Next is the path from D to C. Currently, the shortest path has a cost of infinity. If we look via A, the cost of going from D to A is -2, and from A to C is infinity, meaning there is no path yet, so we will not update it. Now the first iteration is finished. Let's name this new updated matrix as M1, and the updated predecessor matrix as T1. In the next iterations, we will check if we can reduce the costs further by going through other nodes. Since we've already checked node A, let's now see whether we can get shorter paths via node B. And just like the previous iteration, we will not be updating the rows in column of B, as they already represent the direct connections. Also, we will not check the diagonal element, since our example graph does not have negative weight cycles. Now let's see the path between A and C. Currently, the cost to reach there is infinity, meaning no path is known. But if we look via B, first going from A to B has a path with a cost of 2, and going from B to C also has a path that costs 2, giving a total of 4. Since 4 is less than infinity, we will update it to 4 and set the previous node to B, as the path is coming via B. Next is the path between A and D. Currently, the shortest cost is 3, but if we check via B, the cost from A to B is 2, and the cost from B to D is 6. This gives a total of 8, which is more than the current cost of 3. So we will not update this one. And similarly, we will perform the updates. Try pausing the video and solving it yourself. You should get these updated values. Now, this is the matrix M2 and T2. Similarly, we will find the matrices M3 and T3 via node C in the next iteration, and then the matrices M4 and T4 via node D. And once we check the shorter paths via all the nodes, we will stop. Now, we can use these final updated matrices to construct the shortest path from any pair of nodes. Now, let's construct the path from node C to B. Here in the matrix, we can see that the shortest path has a cost of 4. But to actually construct it, we need to look at the previous node in the predecessor matrix, which is node A. So we will add A to the path. Next, we need to find the previous node in the path from C to A, which is D. So we will add D now. Now, this is our shortest path from C to B. This is how to construct the shortest path between any pair of nodes. Now, the algorithm loops over each node once and traverses the whole matrix for each node. So the time complexity is big O of V cube, where V is the number of nodes. And the space complexity is big O of V square, as we use matrices to store the shortest paths and predecessor information. Now, let's see the Python code implementation. Feel free to skip this part if you're not interested. First, we will import the math library. Then, we will define a function that takes the dimension n and the matrix as input parameters. Then, we initialize a variable infinity using the math library we imported earlier. Next, we initialize the previous node matrix with none values. Then, we also create a variable nodes that maps indices to letters like A, B, C, and so on. After that, we loop over the distance matrix, and for each pair of nodes, if there's a direct edge between them, we set the previous node in the previous node matrix to the source node. We then run a loop n times, where n is the number of nodes. In each iteration, we traverse the entire matrix once, and at each element, we check if there is a shorter path. If a shorter path is found, we update both the distance and the previous node matrices. We then loop over the diagonal elements of the resultant distance matrix and check if any element is less than 0. If there is, we indicate that the algorithm fails due to the presence of a negative weight cycle and return none. Otherwise, we return the distance and previous node matrices. Check out the GitHub link in the description box for the complete code.
पहला इंपॉर्टेंट पॉइंट क्या बताता है कि आप हर नोड
Today we're Today Today we're going to learn about the Bellman-Ford algorithm on weighted directed graphs. Let's look at this graph. Since this graph has 6 vertices, we'll run at most 5 iterations. We start with vertex S. From S, we can reach A with cost 3 and C with cost 5, so let's update our table. Next up is vertex A. Now we know we can reach A with cost 3. Looking at the outgoing edges, we see we can reach B with cost 1, so the total cost is 4. Moving to vertex B, from B there are no outgoing edges, so we keep going. Next up is vertex C. We know we can reach C with cost 5. Looking at the outgoing edges, we can reach B with cost -3 and E with cost 5, so we update our table accordingly. For vertex D, we don't even know how to reach it yet, so we move on to E. We can reach E with cost 10. From E, we can reach D, so let's update the table. The first iteration is now complete. We'll run the second iteration, but none of the values will improve, so we can stop here. Now I'll replay the whole process with animation. There's no voiceover during the animation, so watch carefully.
Hey everyone, welcome to today's video. In this episode, we're diving into another classic shortest path algorithm, the Bellman-Ford algorithm. What makes this algorithm special is that it doesn't just work with positive edge weights, it can also handle negative edge weights and even detect negative weight cycles. This makes it more useful than Dijkstra's algorithm in certain situations. Before we dive into the Bellman-Ford algorithm, let's take a moment to revisit the shortest path problem. This is one of the fundamental challenges in graph theory, and you might remember that Dijkstra's algorithm is one of the most efficient ways to solve it. This method follows a greedy approach with dynamic updates. It always expands the node with the shortest known distance and keeps refining the shortest paths to its neighbors until all nodes have been processed. If you're curious to learn more about Dijkstra's algorithm, be sure to check out our other videos on this topic. However, Dijkstra's algorithm has a major limitation. It cannot correctly handle negative edge weights. But what does that mean?
कंफ्यूज कि कौन सा स्टॉक खरीदना चाहिए तो बस ट्रैक पे जाओ, उसके स्टॉक रिकमेंडेशंस देखो और डिसीजन लो.
What does that mean? In some real-world scenarios, an edge in a graph might have a negative weight. For example, in finance, a negative weight might represent a discount or profit in a transaction. In network routing, it could indicate a reduced cost for data transmission. The problem is that Dijkstra's algorithm follows a greedy approach. Once it finalizes the shortest path to a node, it assumes that path will never change. As a result, it can fail when dealing with graphs that include negative edge weights. Let's go through an example. Imagine we have a graph where the distance from A to B is 4, A to C is 3, and B to C is -2. If we use Dijkstra's algorithm, it will first determine that the shortest path from A to C is 3 and never reconsider it. But if we take the path from A to B to C, the total distance would be 4 plus -2, which equals 2, actually shorter. The problem is, Dijkstra's algorithm won't find this because it locks in the first shortest path it discovers and never looks back. So, how do we handle graphs with negative edge weights? That's where the Bellman-Ford algorithm comes in. The Bellman-Ford algorithm, introduced by Richard Bellman and Lester R. Ford Jr. in 1958, finds the shortest paths from a single source node. Its core idea is iterative relaxation, repeatedly relaxing all edges until all shortest paths are determined. Here's how it works. First, we initialize the distances. The starting node is set to 0, while all others are set to infinity. Then, we perform v-1 iterations, where v is the number of nodes, relaxing every edge in each iteration. If a shorter path to a node is found, its distance is updated. This process is known as relaxation. After v-1 iterations, all shortest distances are finalized, unless a negative weight cycle exists. To detect such cycles, we run one additional iteration. If any distance can still be updated, it means the graph contains a negative weight cycle, where paths can decrease indefinitely, preventing convergence. Now, let's walk through a visual example to see the Bellman-Ford algorithm in action. Imagine we have a directed graph with 6 vertices, A, B, C, D, E, and F. The edges and their weights are shown in the diagram, and some of these edges have negative weights. For example, the edge from C to B has a weight of -2, and the edge from D to F has a weight of -1. Our goal is to find the shortest path from A to all the other nodes. To begin, we create a table with 3 columns. The first column lists all the nodes in the graph. The second column shows the current shortest distance from A to each node. Initially, the distance from A to itself is 0, while all other nodes are set to infinity because their shortest paths aren't determined yet. The third column records the predecessor of each node, which will help us later when we need to reconstruct the shortest path. At the start, all predecessors are empty. Next, we list all the edges in the graph to get ready for iteration. Unlike Dijkstra's algorithm, Bellman-Ford doesn't require the edges to be processed in any specific order. The final shortest path results will be the same, no matter what order we check the edges in, though the order may affect how quickly the algorithm converges. Now let's start the iterations, or relaxation process. According to the Bellman-Ford algorithm, we need to perform v-1 iterations. Since our graph has 6 vertices, we'll perform 5 iterations. In the first iteration, we go through all edges one by one and try to update the shortest paths from A. First, we check the edge from A to B, which has a weight of 6. Since A's current shortest distance is 0, 0 plus 6 equals 6. Since 6 is smaller than B's initial distance, infinity, we update B's shortest distance to 6 and set A as its predecessor. Next, we check the edge from A to C, which has a weight of 4. Since A's distance is 0, 0 plus 4 equals 4, which is smaller than C's initial distance, infinity. So we update C's shortest distance to 4 and set A as its predecessor. Then, we check the edge from A to D, which has a weight of 5. Since A's distance is 0, 0 plus 5 equals 5, which is smaller than D's initial distance, infinity. So we update D's shortest distance to 5 and set A as its predecessor. Next, we check the edge from B to E, which has a weight of -1. Since B's shortest distance is 6, 6 plus -1 equals 5, which is smaller than E's initial distance, infinity. So we update E's shortest distance to 5 and set B as its predecessor. Then we check the edge from C to B, which has a weight of -2. Since C's shortest distance is 4, 4 plus -2 equals 2, which is smaller than B's current distance, 6, so we update B's shortest distance to 2 and set C as its predecessor. Continuing, we check the edge from C to E, which has a weight of 3. Since C's shortest distance is 4, 4 plus 3 equals 7, which is greater than E's current distance, 5, so no update is made. Next, we check the edge from D to C, which has a weight of -2. Since D's shortest distance is 5, 5 plus -2 equals 3, which is smaller than C's current distance, 4, so we update C's shortest distance to 3 and set D as its predecessor. Then we check the edge from D to F, which has a weight of -1. Since D's shortest distance is 5, 5 plus -1 equals 4, which is smaller than F's initial distance, infinity, so we update F's shortest distance to 4 and set D as its predecessor. Finally, we check the edge from E to F, which has a weight of 3. Since E's shortest distance is 5, 5 plus 3 equals 8, which is greater than F's current distance, 4, so no update is made. At the end of the first iteration, the shortest distances from A to B, C, D, E, and F are now 2, 3, 5, 5, and 4, respectively, with predecessors updated accordingly. In the second iteration of relaxation, we go through all the edges again, checking if any shorter paths can be found. Just like before, we attempt to relax each edge. By the end of this iteration, some shortest distances update further, such as A to B and A to E, which reduce to 1. However, no predecessor updates occur in this iteration. In the third iteration, some shortest distances update further. At this stage, the shortest distance from A to E reduces to 0, and A to F decreases to 3. The predecessor of F changes from D to E. By the fourth iteration, no further updates occur. This means the algorithm has converged early, and the shortest path results are now final. The final shortest distances from A to A, B, C, D, E, and F are 0, 1, 3, 5, 0, and 3, respectively. Using the predecessor nodes, we can reconstruct the shortest paths. For example, the shortest path from A to B is A to D to C to B with a total distance of 1.
You can now learn chess on Duolingo. Yes, that chess. The one with the pawn and pony. Want to train your brain for speed and strategy? Or crush your friends with a devastating checkmate? Well, giddy up. Come learn chess today.
To B with a total distance of 1. Now, how does the Bellman-Ford algorithm detect negative weight cycles? Let's go through an example. Imagine a graph with 3 nodes, A, B, and C. The edge from A to B has a weight of 1, from B to C has a weight of -3, and from C to A has a weight of 1. According to the Bellman-Ford algorithm, after V-1 iterations, which is 2 in this case, the shortest path distances should have stabilized. But if we run one more iteration and notice that some distances are still decreasing, it means the algorithm hasn't converged. This is a clear sign that the graph contains a negative weight cycle, where distances keep getting smaller indefinitely. Now let's explore the Python implementation of the Bellman-Ford algorithm. This function finds the shortest paths from a given start node to all other nodes in the graph and also detects the presence of any negative weight cycles. It takes 3 inputs: a list of edges, the start node, and a list of all nodes. At the beginning, the function initializes 2 dictionaries: distances to track the shortest known distance to each node, setting the start node to 0 and all others to infinity, and predecessors to store the previous node in the shortest path, initially set to none. Next, the algorithm performs V-1 iterations of relaxation. In each iteration, it examines every edge to determine if a shorter path exists. If a shorter path is found, the algorithm updates the shortest distance and records the predecessor of that node. If no updates occur during an iteration, it indicates that the shortest paths have stabilized and the algorithm can terminate early. After completing these iterations, the algorithm performs a final check. If any distance can still be updated, it indicates the presence of a negative weight cycle, and the function returns a message confirming this. If no negative weight cycle is detected, the function returns the final shortest distances, the predecessor dictionary, and the results from each iteration. Here, we define the nodes and edges based on the graph we discussed earlier. This method backtracks through the predecessor dictionary, allowing us to reconstruct the shortest path from the source node to any destination node. The time complexity of the Bellman-Ford algorithm is fairly straightforward to analyze. The algorithm performs V-1 iterations, where V is the number of nodes, and in each iteration it checks all E edges. Therefore, the overall time complexity is OV multiply E. This means that as the number of nodes and edges increases, the execution time also increases. For sparse graphs, those with fewer edges, this complexity is typically manageable. Now let's compare the Dijkstra and Bellman-Ford algorithms. Both algorithms solve the single-source shortest path problem, meaning they aim to find the shortest path from a given source node to all other nodes in a graph. Dijkstra's algorithm uses a greedy strategy, leveraging a priority queue to always expand the node with the shortest known distance. This approach makes it very efficient. On the other hand, Bellman-Ford repeatedly relaxes all edges to find the shortest path, following a dynamic programming approach. When it comes to time complexity, Dijkstra's algorithm, with a binary heap optimization, runs in O v plus E log v, which is typically faster than Bellman-Ford's O v multiply E, especially in dense graphs with many edges. One major limitation of Dijkstra's algorithm is that it cannot handle negative weight edges, which could lead to incorrect results. In contrast, Bellman-Ford handles negative weight edges and can even detect negative weight cycles, making it more versatile. To summarize, if all edge weights are non-negative, Dijkstra's algorithm is usually the faster and preferred choice. However, if negative weight edges are present, or if detecting negative weight cycles is important, Bellman-Ford is the better option. That's all for today. If you found this video helpful, please like and subscribe. See you in the next one.
The topic is single source shortest path problem. In this video, I'll show how Bellman-Ford algorithm algorithm works and also the drawback of Bellman-Ford algorithm. The problem is, in a directed weighted graph, we have to select one of the vertices as source vertex and find out the shortest path to all other vertices. Let us say if I select vertex 1 as starting vertex, then I have to find out the shortest path to all of them. Now for doing this, already we have Dijkstra algorithm that will solve the shortest path problem. But Dijkstra algorithm will not work if there are negative edges. It will not work properly. It may give correct result, it may not give correct result. So we cannot use Dijkstra algorithm here and confirm that it's giving correct answer. So we want an algorithm which confirms that the answers are correct. So that algorithm is Bellman-Ford, and it follows dynamic programming strategy. So dynamic programming strategy says that you try out all possible solutions and pick up the best solution. So here we want to try out all possible solutions and pick up the best solution. How we will try all of them? So this algorithm says that you go on relaxing all edges.
Today Sensex closed over 1200 points and Nifty 50 closed above 24,000.
Go on relaxing all edges. How many times? All edges, you repeatedly relax them for n minus 1 time. What is n here? N is the number of vertices. Number of vertices are 7. So I should relax them for 7 minus 1. What is the idea here? If from the source vertex, if the longest distance may be of all edges, then total how many edges may be there? So from 1 to 7, there can be maximum 6 edges. So if you are going on relaxing the edges, we may get a longest path also that is of 6 edges. Right? So it will cover all possible paths if you relax all of them for 6 times. So what is relaxation? If I take any two vertices, let us say 2 and 5, and I know some distance of this vertex, the path to this vertex and the path to this vertex also, then I should see that if the path of this one plus this is less than this one. If so, I will change this one. So I will call them as U and V, and I will write down what does relaxation mean. So then once I start using it, I can explain you how it works. So relaxation means what? Between a pair of vertices u comma v, if there is an edge, then check if the distance of u plus cost of an edge u comma v is less than distance of v. If so, then change the distance of vertex v to distance of u plus cost of an edge u comma v. What is that? I will explain you while solving this. Now let us follow the algorithm. What the algorithm says, you prepare a list of all edges. Prepare a list. So which edge I should select first? You select any edge. First you select this one, then this one, or this one, or this one. You select anything, but make sure that all edges are selected. So I'll select them vertex by vertex. So I'll write down the list of edges here. There are total 10 edges. I have taken all 10 edges here, list of edges. Now I have to relax all these edges for 6 times. Now let us start the procedure. For initially, I have to mark the distances of all these vertices. So this vertex, let it be 0. And for all other vertices, mark the distance as infinity. Mark it as infinity. All are infinity. Now start relaxing the edges. Now I will show you how that relaxation procedure works. First edge, 1, 2, 1 to 2. What is the distance of this one? 0. What is the distance of this? Infinity. 0 plus 6 is less than infinity. 0 plus 6 is less than infinity. So change this infinity to 0 plus 6. So make it as 6. The next 1, 3, 0, and this is infinity. So 0 plus 5 is less than infinity. So change this to 5. 0 plus 5 less than infinity. So change it to 5. So first 3 edges completed. Now 2, 5. 2, 5. This is 6 minus 1. This is infinity. So this is 5. 6 minus 1 is 5. This is already changed. You see. 3, 2. So 3 to 2. So this is 5 minus 2 is a 3. So change it to 3. Then 3 to 5. So this is 5 plus 1 is a 6 and it is 5. So that is smaller. Don't modify that one. 4, 3. 5 minus 2 is a 3. So this becomes 3. Then 4, 6. 5 minus 1. This is 4. This is infinity. So change it to 4. Then 5, 7. So 5 plus 3 is 8. This is infinity. So change it to 8. 6, 7. 4 plus 3 is 7. This is less. So change. So most of the changes we have seen first time only. Let us continue. Second time. 1, 2. So 0 plus 6. 6 and 3. So this is greater than that one. So don't change that one. 1, 3. 0 plus 5. 5. That is 3. Don't change that one. 1, 4. 0 plus 5. This is 5 only. No change. Then 2 to 5. 2 to 5. So 3 minus 1. 2. This is 2. That is changing again. So 3 to 2. So 3 is how much? 3. 3 minus 2 is 1. So this will change. 1. Then 4, 3. 4, 3. 5 minus 2. This is 3. This is perfect. 4, 6. 5 minus 1 is 4. Perfect. 5, 7. 5 is how much? 2. And 2 plus 3, 5. This is 7. So change it to 5. Then 6, 7. 4 plus 3 is 7. And it is 5. No change. Let it be as it is. I have completed 2 times. 4 more times I have to do. 1, 2. This will not change. 1, 3. This will not change. 1, 4 also will not change. Then 2, 5. 1 minus 1. This becomes 0. This becomes 0. Right? Then 3, 2. So 3 is how much? 3. 3 minus 2. 3 minus 2 is 1. Already 1. Now no more changes. Then 3 to 5. So this is 3 plus 1. 4. Already it is 0. That is better. 4 to 3. 4 to 3 is how much? 5 minus 2. That is 3. No change. 4 to 6. 4. No change. 5 to 7. 5 is how much? 0. 0 plus 3. 3. This becomes 3. Then 6 to 7. 4 plus 3, 7. That 3 is better. Right? So I'm updating there only. So 3 times I have completed. 3 more times I have to do. 1 to 2 will not change. 1 to 3 will not change. 1 to 4 will not change. 2 to 5. 2 is how much? 1. 1 minus 1, 0. That is not changing. Then 3 to 2. So 3 to 2, 3 is how much? 3 minus 2, 1. 1 is already 1. Then 3 to 5. So this 3 plus 1, 4. That is better. 0. 4 to 3 will not change. 4 to 6 will not change. Then 5 to 7. 0 plus 3, 3 only. 6 to 7. No change. Now this has stopped changing. So what are the results I got? Vertex 1 is 0. Vertex 2 is 1. Vertex 3 is 3. Vertex 4 distance is 5. Vertex 5 distance is 0. Vertex 6 distance is 4. Vertex 7 distance is 3. These are the distances I got. If I continue for 2 more times also, I'll get the same result. So finally, these are the shortest paths. You can observe that. So as I'm doing it manually, I have stopped. But when you write in any algorithm for doing the same thing, it will continue for n minus 1 time. And some graphs may get the shortest path in just 1 time relaxation only, and some graph may relax completely, get the shortest path in the last relaxation. So in this graph, we find that after the third one onwards, there are no more changes. I have taken the shortest paths. So this is how Bellman-Ford algorithm works. Let's get the time complexity of Bellman-Ford. What it is doing? Relaxing all edges. How many edges are there? E edges are there. How many times it is relaxing? V minus 1 time. So this is order of V into E. So if we say V and E are n, so this will be n square. So it depends on the number of edges. If this is a complete graph, then how many edges will be there in a complete graph? A complete graph means there is an edge between every pair of vertex. So total how many edges will be there? N into n minus 1 by 2 edges will be there. So if these many edges are there, then the time will be n into n minus 1 by 2 into number of vertices minus 1, n minus 1. So if you simplify this one, this will be order of n cube. So in case of complete graph, Bellman-Ford algorithm may take even n cube time. Right? Otherwise, minimum time we say it takes n square, and at most it may take n cube time. That is, if the graph is complete graph. Now we'll take a small example and solve it, and also I will show you drawback of Bellman-Ford. A small example, I will take the list of edges. First of all, I will take the edges starting from here. First I will take 3, 2, then I'll take 4, 3, then 1 to 4, then 1 to 2. See, just to make you feel how the relaxation are done, I have taken the vertices in reverse. I should have started from vertex 1. Now let's solve this. My source vertex is 0, and mark all of them as infinity. Mark all of them as infinity. How many times I should relax? There are 4 vertices, so I should relax that for 4 minus 1, that is 3 times. So let us relax all the edges one by one. First 3, 2, infinity minus 10 is infinity only, so that is no change, it is already infinity. 4, 3, infinity plus 3 is infinity only, and is already infinity. Then 1, 4, 0 plus 5, 5 is less than infinity, so change it to 5. Then 1, 2, 0 plus 4, 4 is less than infinity, change it to 4. One time I already have relaxed. Second time, 3, 2, infinity minus 10 is 4, that is better. 4, 3, 5 plus 3 is 8, this is better than infinity, so make it infinity. 1 to 4, 0 plus 5, 5 only. 1 to 2, 0 plus 4, 4 only. 2 times I have completed, one more time I have to complete. Let us check. 3 to 2, 8 minus 10 is minus 2. Minus 2 is smaller than 4. Now you can see that I got the correct answer for vertex 2 now. Then 4 to 3, 5 plus 3, 8 only. 1 to 4, 0 plus 5, 5 only. 1 to 2, 0 plus 4. And that is not greater, not less than minus 2, so minus 2 is better. Let it be as it is. So I have relaxed them for 3 times, and I got the shortest paths. So what are the shortest paths? Vertex 1 is 0, vertex 2 is minus 2, and vertex 3 is 8, vertex 4 is 5. These are the shortest path from starting vertex as 2. So Bellman-Ford has got the answer even when there are negative edges. So this is the answer. If I relax this for one more time and see let us what happens, 3, 2, 8 minus 10 minus 2 only, 4, 3, 5 plus 3, 8 only, 1 to 4 and 1 to 2, all are same. So if I relax one more time extra also, there is no change, that means the answers are perfect.
మీరు బీటెక్ లేదా ఫస్ట్ ఇయర్ ఆర్ సెకండ్ ఇయర్ స్టూడెంట్ నేను చెప్పే ఈ ఒక చిన్న పని మీరు చేస్తే గూగుల్ అమెజాన్
are perfect. Now let us see the drawback of Bellman-Ford. I will take the same graph only, but a small change. The same graph, I will add one more edge, that is 2 to 4, and I'll make it as 5. So this is 2 to 4. Now let us relax them. I have to relax them for 3 times. So quickly I will do it because already till here I was doing it. Let us do. So 0, infinity, infinity, and infinity. 3 to 2, infinity only. 4 to 3, infinity only. 1 to 4, 0 plus 5, this is 5. 1 to 2 is 0 plus 4, this is 4. Now 2 to 4, 4 plus 5, 9, this 5 is better. No need of changing. One time over. Now 3 to 2, infinity minus 10, that is infinity. So 4 is better. 4, 3, 5 plus 3, this is 8. Then 1 to 4 is same thing only. 1 to 2 is same thing only. Then 2 to 4, 4 plus 5 is 9, and this is 5, that is better. 2 times completed. The third time. 3 to 2, 8 minus 10, minus 2. Then 4 to 3, 5 plus 3 is 8, 8 is there. 1 to 4 is 5 only. 1 to 2, 0 plus 4, so minus 2 is better. Then 2 to 4, minus 2, and 5 is 3. This 4 is changing. Right? So this was the third time I have done, and I got this answer. Let me try for one more time. Already n minus 1 time I have done, but let me try one more time and check. 3, 2, 8 minus 10 is minus 2 only. Yes. 4, 3, 3 plus 3, 6. Oh, this is changing. 1 to 4 will remain same. 1 to 2 also remain minus 2 only. And 2 to 4, minus 2 to 5 is 3 only. Minus 2 plus 5 is 3 only. So one more vertex has just now relaxed. That should not happen. After completing for n minus 1 time, I should get the answer. If I repeat it for one more time, if I relax all the edges, there should not be any change at all. If I do one more time, again something will change. See, 3, 2, 6 minus 10, minus 4. So that's what, there's a problem. So why we got this problem? Bellman-Ford is unable to solve this one. After performing for n minus 1 time also, I'm not getting the correct answer. Still they are getting relaxed. So even if I do it without Bellman-Ford directly, if I try to do, I cannot solve it. Reason is, there is a cycle of edges, that is 2 and 4 and 3. So this is forming a cycle. This is minus 10 and 3 and 5. So if I add this 5 plus 3, 8, minus 10 is minus 2. The total weight of a cycle is negative. So in this way, I'll be going on getting the path reduced every time. So there is no end of this one. So I cannot decide or freeze the answer. So if there is a negative weight cycle, then graph cannot be solved. Right? So Bellman-Ford fails to solve the graph if there is a negative weight cycle. Total weight of a cycle is negative. If it is positive, it will work. So if weight is negative, it will not work. That's all. Then, but a Bellman-Ford algorithm can detect. So that's what, there's a problem. So why we got this problem? Bellman-Ford is unable to solve this one. After performing for n minus 1 time also, I'm not getting the correct answer. Still they are getting relaxed. So even if I do it without Bellman-Ford directly, if I try to do, I cannot solve it. Reason is, there is a cycle of edges, that is 2 and 4 and 3. So this is forming a cycle. This is minus 10 and 3 and 5. So if I add this 5 plus 3, 8, minus 10 is minus 2. The total weight of a cycle is negative. So in this way, I'll be going on getting the path reduced every time. So there is no end of this one. So I cannot decide or freeze the answer. So if there is a negative weight cycle, then graph cannot be solved. Right? So Bellman-Ford fails to solve the graph if there is a negative weight cycle. Total weight of a cycle is negative. If it is positive, it will work. So if weight is negative, it will not work. That's all. Then, but a Bellman-Ford algorithm can detect if there is a negative weight cycle or not, because after performing for n minus 1 time, so we can relax one more time and check if the vertices are getting relaxed. If any of the vertices is getting changed, then it means there is a negative weight cycle. So that's all about dynamic programming Bellman-Ford algorithm. The problem is 0-1 abstract problem. In this video, I will explain what is zero knapsack problem and how it can be solved using dynamic programming. We will understand its approach. Next, I will show you a tabular method for solving this one. Then also I will show you a sets method for solving this one. So there are two methods. We will see both the methods. First of all, let us understand what the problem is. Here I have some 4 objects. For each object, there is some profit and there is some weight. And there is a bag of capacity M, that is 8 is given. The objective is to fill this bag with these objects. So can I put them all? See, the capacity 8 is 8, but the total weights of all these objects is 14. So all objects cannot be filled in the bag. So I have to carry few of those, some of those objects, there is a subset of those objects, and I have to carry them and sell them at other place. So once I sell, I get this profit. So I have to fill the object such that the total profit is maximized. And I have to give the solution in the form of a set for each object. Like, for example, this is included and this is not included, or not included. Like this, I have to write down which one is included or not included. So it means I can write down each xi either 0 or 1. Means the values can be 0 or 1, but not fraction. So it means that the object that I'm going to carry are not divisible, breakable. So I cannot take the fraction of that object. So this means these are some solid objects. Maybe a mixer or microwave oven or a rotor. It can be something like this. So which I cannot take a half of a mixer in the bag. So these are indivisible objects. So either I should carry the whole object or don't carry it at all. So I have to carry the object such that the sum of their profits